Good morning again. This is the second part of the subject that I wrote in the paper. This is the paper that I wrote. I showed you last time about, and I think it's an important important remark in doing science in general, and the honesty of science that I'll come back to later. In the previous video, I told you something about the statistics and the Gaussian curve, or the skewed Gaussian curves both, and something in reality is coin tossing, which also shows some statistical Gaussian curve-like behavior, albeit in addition of two skewed Gaussian curves, as was the remark. Now, you may put the comment that, well, if you want to cover it all and also the extremes, you just have to keep on tossing those coins until one moment in time these coins will all fall head up or tails up. Well, yeah, if you have enough time, that may happen, yeah, but that's the point. What we do have, and that's why I'm referring to it, there is always a time limit. And the 100 tosses, or in the maximum I used 311 tosses, it represents a time limit. Now, theoretically, yes, you're right, you have limitless time, theoretically, but in reality, you don't. And yes, I could have tossed 1,000 times, I could have tossed 2,000 times, and so on. But it does not represent reality. Reality is that we have a limited time. And now, as you know, I am a Christian, I'm a creationistic Christian, and I believe that the earth is no older than 6,000 years. But okay, suppose that even the secular guys are right, and the universe is about 14 something billion years old. Nonetheless, in whatever kind of process you are looking at, there is always a limit in time, and that's the whole point of this thing. So yes, mathematically you are right, you can toss a lot of times, you can toss a lot more times, but that's the theory, that's not the reality. And we are talking here about physical reality, so the mathematical probability opposing the physical reality of it. And yes, if I take enough time, suppose a theoretically limitless time, yeah, then you might be probably right, but that's not the point. We are stuck in the time that we have, and whether you believe in a 14 billion year universe, or you believe in a 6,000 year old universe, there is always a limit of time, and that's the whole point that I try to make. Okay, now let me see. This video is about the reality or the limits of the numbers that we have, the limits of some physical things. And I'm going to speak about, in this case, pi and the number of Euler, E. Pi 3.14, something, etc. And the number of Euler, 2.7, 18, blah, blah, blah. Now, these both numbers, you can calculate them with all kinds of formulas into the billions and trillions of digits. That's true, that's mathematically correct. I mean, you can use some formulas. What is it? I don't know if I have it here. No, I don't have. And I didn't use it. It's one in my other papers. Am I right? Let me see. Yeah, I didn't use it over here. But that's okay. That's okay. There is theoretically, again, no limit to the numbers you can calculate with pi or the number of Euler E. But let's look at the physical reality of that, and that's why I turn to the boring board. Yeah? Okay. Again. Okay. Now, I have to take the pen of mine. Okay, if you look at the smallest parts, actually I'd like to move it out a little bit, right on here. Okay. This is from the atoms to the size of the universe. And now the size of an atom is somewhere in the 10 to the power of minus 9 meters. Yeah? The size of the nucleus is somewhere in the order of magnitude of 10 to the minus 15 meters. Now it turns out to be that we are able, in the current ability to measure distances is in the order of magnitude of 10 to the minus 20 to 10 to the minus 21 meters. Okay, let's stretch it a little bit up. Let's suppose that in the next 5 years we are limited. We're going to be able to measure 10 to the minus 24 meters. I take this number for the reason I'll explain in a moment. Now, the universe is as it is being measured 92 billion light years, which is not a time reference but a distance reference, and which is about 8.704 10 to the 26 meters. Now, if you take from the smallest to the largest particle, from the smallest particle to the biggest size, which is the universe itself, there is 10 to 20 minus 24, 10 to the 26. So there are 50 orders of magnitude in difference. That means if you want to do calculations in the physical reality, I mean, both represent the physical reality. I mean, the atoms represent a physical reality, and the universe represents a physical reality. But that means that if you know pi, pi to some amount of digits, then the maximum you have to you can use for being accurate, nonetheless, is about 50 to 100 digits, which is more and more than enough. And in order to calculate in all kinds of accuracy, in what you know, and sleep over it quietly without being in trouble over, well, is it accurate enough? Well, 50 to 100 digits is more than enough. Yeah? Well, now it is physically real that pi is usually used in the combination of the Euler's numbers in many physical formulas. The number of pi and the number of Euler E is being used frequently. For example, in the Gaussian curve, which I showed you in the last video, there is E and pi is being bothly used to represent measurements, the statistical measurements, because and I have to peek a little. I don't know it by heart. If you see the Gaussian distribution curve, it's f fx is 1 over sigma or s square root 2 pi, there you have it, times e, the Euler's numbers, half times minus half times x minus mu divided by sigma squared. So here you both see both e and pi are ending up in the same formula. Well, this is only statistics, and statistics represent, of course, measurements, physical measurements. So both e and pi are many times ending up in physical formulas, or formulas that represent some physical things in nature. That means that also for the number of E, Euler's number, about 50 to 100 digits is more than enough accurate to use in science. And that's the whole point that I try to make now. Now, On top of this, we're talking about atoms here. Yeah. There is something like the Heisenberg uncertainty principle, which says delta X times delta P is always bigger or equal to H bar divided by 2. Or delta T times delta energy. It's the same thing. Yeah. It's also bigger or equal to H bar divided by 2. That's the lumpiness of nature. And so there are, nature has limits. So yes, you can, mathematically speaking, you can have trillions and trillions of digits of pi or the number of Euler. But that's limited, and statistically and or no, numerically, mathematically, those numbers are correct. Yeah, that's true. I mean, you can calculate pi or the number of e to so many trillion digits, and mathematically that is correct. But there is the limit of nature, the nature's limit by the sizes of the universe and the sizes of the smallest particle that limit us in the physical usefulness of those numbers. And that's the whole point that I try to make. That's the second point that I try to make. So here also you see, okay, the mathematical correctness compared to the physical reality and the physical limits, in which also the quantum mechanical limits of lumpiness. Nature is lumpy. I mean, it's divided. It is quantized, or quantized, or whatever kind of way you want to pronounce it. That means that that nature has limits, physical limits, which we for now, as most certainly, we cannot go beyond. And that's actually the second point that I try to make in this video series. Okay, we go up to the next video in which I want to make a statement as well. Okay, thanks for watching so far, and see you in the next video. Hasta la vista.